Hi, in this segment I'd like to discuss what it takes for a new design concept to become reality, and then go through a conceptual design case study to show the process of problem definition, ideation, and bringing ideas to the point of prototyping for evaluation and hopefully a minimum viable product, an MVP, that can sell. The automobile has been a world-changing set of technologies. When you look at old photos, you realize though that the basic design of the car hasn't changed much in 100 years. Sure, there are new features and great innovations under the hood in materials, construction, controls, safety, and reliability. But the basic idea of a horseless carriage remains the same. However, this is changing because of several converging technologies and a global need to reduce reliance on burning hydrocarbons, for transportation anyway. These technologies are high-capacity electric batteries, renewable electric power production, ride-sharing networks aided by portable digital telecommunication systems, and automation. An autonomous electric car connected to distributed users used to be science fiction. Now it's becoming a reality. But how to mesh current technologies in transition remains a huge challenge. This is an example of the technology S-curve, in which a technology reaches a pinnacle of performance just as it gets knocked off its perch by a new technology that meets evolving needs better. Sailing ships, typewriters, and fountain pens are all examples of dominant technologies that disappeared from commercial use when a true alternative appeared as demand was changing. Great technologies can continue to evolve provided a market niche exists, reminding us that technology always has to address some need. Now, I'd like to introduce a case study. I've been working in robotic systems development for a long time. A couple of my grad students started a company to produce amphibious robots for environmental monitoring. They had a lot of trouble making systems that people wanted to buy because their potential customers couldn't really imagine how to use robots in field conditions. And these conditions are tough, hard to navigate through, and very hard on equipment. The company went through several iterations of prototypes because there was no theory of terramechanics for dynamics of driving through extremely variable soils and mud, and little that has been reported in the literature. Different drivetrains were tried, motors weren't sized properly. It was a bit of a mess, but they learned and persevered. And so did I. Once a series of changes were made, performance and reliability improved, and one client agreed to a field trial. This was a critical time for the company because it was low on cash and still hadn't made any sales in its flagship product. With careful attention to building only what the client needed and a break in the cost of production by using additive manufacturing rather than custom welded fabrication techniques, a successful trial of an amphibious autonomous robot was achieved. That system was a minimum viable product, and that MVP led to other potential customers seeing what was possible, and now other clients have ordered units as well. And now I'm doing research on the dynamics of terramechanics for amphibious robots so that performance becomes more predictable. Meanwhile, the company is busy taking the design of that MVP and turning it into a production model, hiring more staff and paying close attention to what the client really needs.